go. Okay, so there's a few things some people were asking me about, and I wanted to clarify regarding the finite element method. There are some important details I wanted to clarify. So first, let's recap. So the finite element, we talked about the finite element discretization of the kinetic energy, right? It was the easy stuff or easier stuff, the mass matrix and stuff. And there is finite element discretization of the potential. So we call the potential like E of x, where the E is like elastic potential or energy function, and the x is the state vector, right? The x is still R3n vector. Let's assume we are in 3D. You could do it in any dimension. Typically 2 would be the other popular dimension, but let's make it more concrete. And what you do a sum over T, which in my case are tetrahedrons or tets. And you have the material function, and you have the deformation gradient operator GT, which takes the state and produces a vectorized 9×9 deformation gradient. I'm going fast because we already had that. So this GT is a 9×3 matrix, and this GTX, that's nothing but a vectorized deformation gradient corresponding to the tet number T. And the psi of T, that's the material model, which means that's a function that takes a 9-dimensional vector, the vectorized deformation gradient, and returns me non-negative scale. That's what I mean by this plus. It cannot be negative. And that's kind of, you can interpret it as the amount of stored potential energy due to the deformation corresponding to the deformation gradient. So that's what we had before. That's the standard finite element. I should even say linear finite element, because we are assuming those are tets, right? That's what we had before. That's why this operator is just linear, and you don't have to do any funny quadrature business. The quadrature basically boils down just to, oh, and here is the term I forgot, right? That was this WT or whatever you want to call it. It's the term for the rest pose volume of the tet. Okay, so that was just to remind you what we had before. Does that sound kind of familiar? Okay, and the few comments I wanted to make here is that in practice, you will be minimizing this, either this alone in quasi-statics, subject to some constraints, which are known as boundary conditions, usually in finite element methods, or you will mix it with some inertial term, like when you're doing implicit integration, but still the hard part will be essentially minimizing this, right? And that's what we covered. To minimize this, you will end up doing Newton's method. So we'll be computing the gradient and the Hessian and all these things. So what you need to know is how to differentiate these functions, okay? And the general form of, so basically the question is how to differentiate. Differentiate E. Because when you want to get a working implementation, you need to take your particular material model and figure out what is the gradient and the Hessian of this E term, okay? So let me just make some comments on this. So if you want to compute the gradient of the potential, maybe you should actually write what is the type of that potential, right? It's a function that goes from 3n to r plus, and that's essentially the total stored deformation energy in all of the elements as per the current deformation represented by x. Okay, we assume that the rest pose is not changing. We assume that that's built in the GT operator, the rest pose. All right, so to compute the gradient, we just apply the chain rule, and the chain rule tells us that the gradient will be exactly this. It will be, we need to take the gradient of the material model, and that gets applied to the GT of x. This is T. Okay? So this GT transpose, that's exactly from the chain rule, right? Because we are differentiating with respect to x. So this GT pops out. You can check that the transpose makes, oh, I made a mistake. This was supposed to be 9/3n, right? Because the GT takes x as input. That's why I kind of like to write the dimensions, because you can check it. It should all check out. So let's check it out here. So G transpose is gonna be a 3n by 9-dimensional matrix. Okay. What is the type of the gradient of psi? So the original one, the psi t was r9 to r plus. What's gonna be the gradient? the type of the gradient. Like if you think about it in terms of code, right, then you have a function, psi, you would probably like say in your code you would have psi, right, and it would have some input and would produce some output. In this case, the output would be just a float or double, a scalar. What it would be in this case? Any ideas? So the gradient means that's the vector of partial derivatives of this function with respect to all its arguments, right? We were using this many times. So in terms of types, what is it returning? How much memory do you need? So it's R9 to R9, okay? Why? Because it's a vector of partial derivatives. So that means the psi t by, if I call the first variable x1, right? This is just a scalar function. I can differentiate by all of the arguments. There is 9 arguments total, so I just differentiate by all of them. This would be x9, okay? And I put it all in a column vector, and that's the output, right? This input means that for every x, I will get a different gradient, okay? There's one exception. In some case, I get the same gradient no matter what x it is. In what case is that? When psi is linear. If psi was linear, then the gradient would be constant, right? But generally, if it's not linear, then the psi depends on the x, and that's why you need this input. That's why this input R9 thing here. I mean, it's kind of the same thing as here. Okay, so the gradient that is a 9 by 1 thing, right? This whole thing is a 9 by 1 thing. And so this is a 3n by 1 vector. If I sum them together, I still get a 3n by 1 vector. Okay, so that makes sense, right? Because the e was a function from R3n to R plus. So the gradient of e needs to be a function that takes a state and gets me also a 3n dimensional vector. Okay, so that all checks out. So the only thing you need to figure out here, what is the gradient of your material, and that depends on the specific material model you are using. Okay, so you have to, so we had that's what we talked about the last time, I guess 2 weeks ago now. The different types of material models we talked about. There's the linear elasticity, there is Santvenon-Kirchhoff models, there is quantitative elasticity, there is Nel-Hookian elasticity, and there is an entire zoo of different models, Ogden, Muner, Rivlin, all these things you can find in the literature. All this means is different psi functions, okay? And to be able to compute the derivatives, you need to figure out what the derivatives of the psi functions are, okay? The good news is that this is kind of simple or simpler because it only has the 99 degrees of freedom, okay? So that doesn't scale up like this n that can go to 10,000, 100,000. If you do scientific computing, you can go even higher and use a supercomputer or something. But this will still be just per element. Okay, so now we still need to do the Hessian, so that's one order higher. So that just means applying the chain rule one more time. So if you do this, oh, I forgot the WT, that's the scaling by the rest post volume. That always needs to remain there, okay? And if you do the chain rule again, then you get a formula that looks like this. It's quite neat, actually. You can appreciate some nice symmetry. That basically means that we are differentiating this expression, so this thing stays there, that's just a constant, but now the chain rule kind of pops out the GT to the other side. And that's so that the dimensions actually work out, so let's go through that. So this is still 3n by 9, right? Now this thing here, that's the Hessian of psi t, okay? So in this case, that will be a 9 by 9 matrix. And the GT, that's going to be, of course, a 9 by 3n matrix, okay? So this thing I can continue, right? I can erase this. And I can continue with writing the Hessian of psi of t, right? And that still takes the x. It always depends on the input parameter. But now it produces a 9 by 9 matrix, okay? And that's the matrix of the second partial derivatives. Is that clear? Or do you want me to write it just like wrote the gradient? Why not? If I already wrote the gradient, I can write this too, right? But it's kind of the same. So it's the second partial derivative of the psi t. The t just reminds you that it depends on every single tet, so every tet can have a different one. and it gets differentiated by x1, x1. Now it goes here, so this will be psi t differentiated by x1, x9. It's a symmetric matrix because it doesn't matter if you supposed to be another differential x9, x1. And finally you differentiate by x9 and x9. Okay, it is symmetric because from calculus you know that this must be exactly the same as this. The order in which you differentiate doesn't matter, so this matrix is symmetric. And what I wanted to put here was the Hessian, right? So again, this is something you have to figure out for every single material model separately, because this of course depends on what exactly the size. But the good news is this is just a 9 by 9 matrix, okay? No matter how many elements in your simulation you have, so that's kind of good. And again, the dimensions kind of work out, right? Because if you put it together, this is a 3n by 3n matrix. So if I sum 3n by 3n matrices, I also get 3n by 3n matrix. So this whole thing, I can write it here, is an operator that takes the input and produces a 3n by 3n matrix as an output, okay? And that's exactly what you can then plug into Newton's method or modify Newton's methods, and then it should work if you got it all correctly. By the way, with this formula, there is one caveat, and that's kind of one lesson learned the hard way. It's easy to implement this in a horribly inefficient way, okay? So let me ask you something. How many non-zeros is in this GT matrix? How many non-zeros does the GT matrix have? Altogether, it has 9 by 3n elements, right? So 27n elements, and n is the number of your vertices. That can be 10,000 easily, okay? But it's mostly zeros. How many non-zeros are there? Do you want to guess? Okay, so let me remind you what the GT was. Maybe it's not fair to request you to remember this. So the GT looks like this. This is the inverse transpose of the rest pose edge matrix. This is the selector matrix, and that's just a Kronecker with I3. That's kind of the result of this vectorization, how I convert it to the 9-dimensional vector. So this thing is just a 3 by 3 dense matrix. If you remember when we talked about finite elements, that's the matrix of the edges of the TAT in the rest pose. Okay, it was the x1 minus x4, x2 minus x4, x3 minus x4. It's a 3 by 3 matrix. I take the inverse transpose of that. Now the ST, if you remember, that is a 3 by 9 matrix. 3 by n matrix. And the matrix looks like this. It has 3 rows, right? And it's essentially a selector, subtractor matrix, which basically does exactly what I just said. It does the subtractions of the vertices. Okay, so if this is the index of the first vertex, this is the index of the fourth vertex, then this matrix applied to some vector says subtract this guy from that guy and return me the result. Okay, zeros everywhere else. Okay, this means the ones are just on these spots. Okay. So the ST matrix has only 6 non-zeros, okay? So from this we can figure out exactly how many non-zeros the GT has. So this is a dense 3 by 3 matrix, right? And gets multiplied with this matrix. So you take every row and multiply with every column. So this, if I'm not mistaken, this looks like this is going, so in the output, this can become dense. So you will have 4 columns. Each can have 3 non-zeros. So this looks like this will have a total of 12 non-zeros. Does that make sense? Because I'm multiplying a dense 3 by 3 matrix. There might be some zeros, but who cares? Let's just assume they're all non-zeros. Multiplied by 3 by n matrix, I get a 3 by n matrix back. But I'm saying it only has 12 non-zeros. Why? Because the ST has zeros almost everywhere, right? So if I'm multiplying anything with zeros, I get zeros back, right? The only place where I can get non-zeros, where there were zeros in ST, are these spots here. Which might get filled in by the multiplication. Okay, so altogether 12 non-zeros. A question for you, if you remember the Kronecker product, how many non-zeros is gonna have the whole GT now?
It's still be 12, right? Wouldn't it still be 12? You just factorize them.
So this is 12, and what this does, this takes the 3 by n matrix and upgrades it to a 9 by 3 n matrix, right? Every element becomes an identity matrix.
So then you have 36.
Exactly, yeah, times 3. So this whole thing, exactly 36 non-zeros. So that means this GT matrix can potentially be huge, right? It can be 9 by 30,000. But it always will have only 36 non-zeros, okay? And if you just implement this naively, if you just like code up this formula, and even if you use like a really good library like Eigen, which is optimized super well, you can get a terrible performance. And to explain you why is I need to go into the details of sparse matrix data structures. Okay, so let me talk about it a little bit. Sparse matrix data structures. Have you heard this before? Like there are the buzzwords like CRS, compressed row storage, or compressed column storage. Did you have it in some other class? Anybody? You did? Which class? I'm curious.
Not class, but using Eigen.
Oh, not in a class, but you saw it in the Eigen documentation. Okay. Okay, so let me. Most of you haven't seen it. You can definitely Google it up, but it's kind of important because if you let me first explain what it is, then I'll explain why it's important. So basically, to store, how would you store this, right? What's a good data structure for storing sparse matrices? The idea is that I don't want to be storing the zeros, right? What's the first thing that comes to mind how to store a sparse matrix?
Okay, hash or a dictionary or something.
Okay, and
I just have the keys be the addresses that are known.
Sure, yeah. Okay, so let's be concrete. So I have a sparse matrix, right? There are some non-zero elements. There's like a few non-zero elements over there, right? So each of them has a row index and a column index, right? I and j, and also has some value, right? So they're saying you can create basically any data structure which you will key with the I and j and will give you back the value, right? Yeah, and that's perfectly valid. Yeah, actually, the simplest possible thing you can do is to just store triplets. You don't even have to put it into a fancy data structure. You would typically want to do that so you have a quick access, right? But if you just wanted to store it, you can just put I, j, value, triplet, and you would have a bunch of them. For every single non-zero entry, you would have one triplet. You would have a list. And that's the most basic format for sparse to communicate sparse matrices, right? Even if you go to Eigen, there is a way to build a sparse matrix from triplets. In MATLAB, the same thing. That's the most basic thing to do. That's one way, by the way, you can implement all these things, right? Like if you want to create this matrix ST actually, right, you can just figure out the indices of these ones and minus ones, and then just call eigenfunction built from triplets, and it will do that, right? Now, as you already realized, the triplets are not enough because I need to be able to quickly look up values, right? But the hash maps and the stuff that's already a little bit advanced. And the CRS is a little bit more basic, and it turns out that's well suited for matrix operations. Like the thing that you will be doing quite frequently is matrix vector multiplication, for example, that you have a sparse matrix A and you are multiplying it with vector X, and you want this to work fast, okay? It turns out that you don't even need a hash table for this because hash table has some overheads, right? There can be some collisions. You need to like somehow figure out how to deal with it. Sometimes you want to also implement this in graphics hardware and like GPUs, right? Because especially if you go to like extreme scale of things. So a good compromise between the triplets and some fancier data structure is this compressed row storage data structure. And what it means, maybe it's easiest to explain on an example. Let me draw an example of a sparse matrix, 0, 0, 0, 0, 3, 0, minus 2, 0, 0, 0, whatever. I'm just making up the values, 5, 6, 7. This matrix, by the way, is not sparse enough. This is just as a textbook example kind of thing. So the idea is essentially to have three buffers: one buffer for the actual values, another buffer for the column indices, and a third buffer which for every row tells you where to start in the other two buffers. Okay, so in this case, the first buffer, that would typically be called just A as the values of the matrix, that would be just really the values in row major order. Okay, this is the compressed row storage. So I go by rows and I see 5, minus 1, 3, minus 2. So I just jot it down: 5, minus 1, 3, minus 2, and then 5, 6, 7, right? That's where the compression happened. I just discarded all the zeros. Then you need another buffer, because now you also discarded the information about in what column these values were. So you need another buffer, which is sometimes called JA. And for each of the elements, you store the column index. Okay, with the rows, we will deal in a moment. For now, we will just store the column indices. So it'll be 0, this will be 1. Then the 3 was 1, right? Then the minus 2 was 0, 1, 2, 3. And this was 0, 1, 2, 3, 4, if I assume zero-based indexing. And the last funny thing is the IA structure. So that tells you for every row where you want to start. Okay, so the first row, you start at 0, because that's where the matrix starts. Okay, and if I'm looking up second row, then I need to skip these first two guys. Okay, so I essentially need to skip these. So I put there 2. Okay, because if I'm looking at row number 1, or the second row, I guess now I'm assuming zero-based indexing, because that's what you usually implemented in C++. So you skip the first two elements and you start looking here. Okay, and the last one would be 4. Because you skip the 4 values to get to row number 3, or second row. Confusing myself with 0 or 1-based indexing, but that doesn't matter. And sometimes it's useful to kind of slightly simplify your coding to put there the total number of all elements as the last one. Okay, that would be like, you kind of technically don't need it, right? Because you don't need access anything after the matrix, but the last one could be the total number of non-zeros, right? Because you see the pattern, that's the number of non-zeros in before the matrix started. So that's 0, number of non-zeros in the first row, the number of non-zeros in the first 2 rows, number of non-zeros in all of the rows, so the total number of non-zeros. Okay, then there are like variations, right? Then you could say, well, the 0 is kind of silly, right? So we can just get rid of that and just start. So now this nicely matches the number of rows of the matrix. So this is the compressed row storage format, which is quite popular. That's what I think IGAN uses by default. And the nice thing about it, if you want to do a matrix vector multiplication, then it's very convenient, because you just do a scan through these things, and it's quite easy to implement. It would be easier than like a hash table, because you don't have to be looking it up over and over again, because you go by rows anyway, because this thing, the matrix vector multiplication, takes one row at a time, right? So this nicely suits this data structure. There is also compressed column storage, okay? Compressed column storage, which is the same idea, except that the matrix is effectively transposed, okay? So instead of going by rows, as we went here, we go by columns. Same idea, okay? So now this index, these buffers will be the same. This will be storing the row indices as opposed to the column indices, and then this will be telling you how many non-zeros in all of the columns you had. Okay, so it's the CCS is the CRS for the transpose matrix. And now here is the reason why I'm explaining this, because if you just go ahead and blindly implement this, Kind of goes back to what I was saying a while ago, that you need to be mindful about the linear algebra, okay, the numerical linear algebra, and how does it actually translate to data structures, and what the computer has to do at the end of the day in terms of fetching data from memory and floating point operations. So let's see. So if I use the default compressed row storage for my GT, is this going to be efficient? And what if I use the compressed column storage instead? Does it even matter? Is there a difference in performance? So if I want to implement this exact formula, right? Now I'm telling you that it matters which of the two you actually pick. And it matters a huge amount. The trick is, and that's kind of the one thing I wanted you to remember, the trick is if you do the compressed column storage on this matrix, this is a 9x3n matrix, okay? It can be 9 by 30,000 matrix. It only has 36 non-zeros, okay? But if you do the compressed column storage, you still need to allocate ON memory, right? Because there's this index structure here, and that's the number of columns in the case of CCS. Okay, it will be the number of rows in CRS. So in this case, the CRS is fine because the number of rows is 9. Well, that's okay, right? But in the number of columns 3n, that is not okay. Okay, because that can be 30,000, and that's 1,000 times more than the number of non-zeros. Okay, so if you are not careful, no matter how well-optimized library you are using, if it uses the wrong type of storage for sparse matrices, this can be 1,000 times slower than it needs to be. And that's not exaggerating. That really it will be that slow. Okay. So I guess that's just another lesson from the chapter of be careful about the numerical linear algebra, and just the fact that you are using eigen or MKL, that doesn't automatically mean that you will be doing it fast. Okay, so that was one remark. I hope that made sense. There is another one, and that has to do with definiteness fixes. That's the one thing I promised you to explain once we have covered finite elements, so now is the time, right? So from when we talked about Newton's method, you know that in FIS-based, more often than not, the objective functions will be non-convex. We are optimizing. Which means that let's just talk about the potential to make it simpler. So that means that the Hessian of the potential function can be indefinite or singular. Okay. In neither of the cases, Newton's method is going to work. Okay, if it's singular, you cannot even compute the inverse. That just doesn't exist if it's a singular matrix. If it's indefinite, you actually can compute it, but you don't get a descent direction. You get an ascent direction, or you can get an ascent direction. So that's kind of even worse, that like your code will happily run, but it will actually do the wrong thing. Okay, and we talked about this, right? And we said that the one solution for that is to add what? Do you remember? It's to add a multiple of the identity matrix. Okay, that's the simplest definiteness fix in statistics. That's called Tikhonov regularization. It's a very basic way to fix that, because if you pick the C is just a constant greater than 0. If you pick the C large enough, then all your indefiniteness or singularity problems go away. So that's what we discussed before. That's how you can cure the problem of non-convexity, which manifests itself as indefinite or singular Hessians. By the way, this Hessian is exactly this thing. Okay. But you might kind of see what is the limitation, what is the weakness of doing it this way. Imagine you are simulating some like large mesh, some bunny or something like this, okay? And you are doing some funny animations too. Maybe you like stretch the one ear of the bunny or something like this, okay? So the rest of the bunny is still like undeformed, but one ear of the bunny got stretched a lot, okay? okay? So in the one ear, there is something funny happening, and as a result, you get indefinite Hessian, okay? Well, then from what we have before, aha, now I need to choose C large enough so that this whole sum is a positive definite matrix, okay? But that seems wrong, right? Because this identity, that's also a 3n by 3n matrix. So that means that's going to affect all the elements, right? That's going to affect the entire body of the bunny the same way it's affecting the distorted ear, okay? So that doesn't seem right, that kind of all of the finite elements, all of the tats in our case, should be penalized the same amount, even though there's just like a few guys who are kind of responsible for the indefiniteness. So that's why slightly better definiteness fixes were invented, and that's, I guess we can call it like per element definiteness fix. And that looks like this. That means that we know what the form of the Hessian of the potential energy looks like. It always looks like this. This can vary depending on what exactly the material model is, but for linear finite elements, it's always going to have this structure, okay? So what we can do, so we don't penalize the good guys, we only penalize the bad guys, is to do the definiteness fix on this sum, okay? So let me maybe copy it quickly over. Let me maybe, so basically we are looking still at this, right? So that's the sum of T of WT, GT transpose, the Hessian of the material at GTX and now at GT. So the idea is to apply the definiteness fix just to this 9 by 9 matrix, okay? Because that is sufficient, right? It's sufficient to let me call this something. Let me call this H of T. Okay, it's a 9 by 9 matrix. And then you can say that the definiteness fixed version is going to be WT GT transpose and then some H T with a tilde and GT. Okay. Where this HT tilde is a definiteness fixed version of the HT. And what do I mean by definiteness fixed? That means that I make sure that this matrix HT tilde is positive definite, okay? Or at least positive semi-definite. It's a little bit easier to explain, positive semi-definite. By the way, this HT, that's the only place where the indefiniteness can come in, okay? Because if this thing, if all these HTs were already positive semi-definite, then the whole Hessian needs to be positive semi-definite. Is that clear? Or let me explain that. So one way you can test for positive definiteness is that you take an arbitrary vector, you do the quadratic form, and if it's always greater or equal than 0 for any vector v, then it implies that A is positive semi-definite. Okay, that's the definition. We also assume that the A is symmetric. If it's not symmetric, then you can just replace it with the symmetric part, and it's still the same thing. Just assume it's symmetric. The Hessian definitely is symmetric no matter what. You don't have to worry about that, unless there is a bug in your code, which you have to worry about. Okay, so if we do this test on the Hessian, if we do the VT, where V is some arbitrary vector, okay, that's the for every V in R3n, then we get this. And then we can write as the sum of the WTs, right? And there is PT, GT transpose. Here is the Hessian matrix. Now there is GT and V, okay? Now these things, they have to be non-negative, right? Those are the rest-post volumes of the tats. The volume cannot be negative. And what you can see here is that this, so this is just some other vector, okay? Or let me write it like this. This is the sum over T, WT, and then I can say, let's call it, I don't know, Y, okay? Y transpose HT Y, okay? Where I just say the GTV is Y, okay? So Y transpose is V transpose GT transpose. Make sense? I could give it a subscript T to make it clear it still depends on each particular tetrahedron, right? Now, if HT is positive semi-definite, then this whole thing has to be greater or equal than 0. This is greater or equal than 0, well, then the sum has to be greater or equal than 0, right? So the whole thing is positive semi-definite. So indeed, the definiteness fix amounts to making sure that these 9 by 9 per element Hessian blocks are positive semi-definite. Okay? And how can you do this? Well, if you are computing these things, which you are computing them if you are building your Hessian, okay? So you can just run eigendecomposition on this. That's not a big deal because now we are talking about 9 by 9 matrix. Okay, if it's a 10,000 by 10,000 matrix, the eigendecomposition can get slow. But if it's 9 by 9, it's not that big of a deal. And by the way, for specific material types, there are ways how to further optimize the eigendecomposition because these matrices are not arbitrary. So you can write, and now we are getting into like the more recent research stuff. I think this was like 2005-ish done by Joe Taran and Eftichios from Stanford. I think they first used these definiteness fixes in graphics. I wouldn't be surprised if mechanical engineers had it before, but I know the graphics literature. But what they did, it's kind of just like a speed up trick. Okay, you don't have to worry about it if you in your first implementation of this stuff. All you need to do is to compute the eigendecomposition of this, and then look if you have some negative eigenvalues, and if you have some negative eigenvalues, clamp them to 0. That will make sure that your HT matrix with tilde, that means the clamped eigenvalue with the clamped eigenvalues, that makes sure that that is positive semi-definite, and you immediately know that the entire thing is positive semi-definite, so you have definiteness fixed it. And the good thing about this is that now you are not penalizing the good guys, the undeformed elements, they are not being changed at all. You are only applying the definiteness fix where it was necessary. Only for the elements which happen to give you the indefinite Hessian, per element Hessian. Okay, this 9 by 9, that means that because it's per element, or specifically per deformation gradient, really, right? Every element, every tetrahedron has a deformation gradient to it. The deformation gradient vectorized, it's 9 numbers. This is the Hessian corresponding to the specific finite element. Okay, so that was remark number 2. And remark number 3 is projective dynamics. Some of you are asking me what projective dynamics is. That's a recent technique which is very useful for real-time physics-based simulation because it's faster than the traditional Newton's method in case you don't need super high accuracy. Okay? So, projective dynamics. Having explained all this, I can explain projective dynamics incredibly simply. Okay, there is an entire paper. There's actually several. Tintin has a new paper on like a generalized projective dynamics. And now with all this set up, you will be shocked how simple projective dynamics is. There are actually several formulations of projective dynamics in the original 2014 paper. It's fairly convoluted, so it's not easy to see how does it relate to this formulation. That explained better in the new paper, which Tintin will be presenting at SIGGRAPH this year. But I will just give you the short version of the story. Projective dynamics is a quasi-Newton method which corresponds to an extreme version of a definiteness fix. Okay. By the way, just terminological thing, all these definiteness fixes you can interpret as quasi-Newton methods. Okay. I think we talked about this before. We talked about Newton's method. Quasi-Newton means that instead of the exact Hessian, you use some modified version of the Hessian. That's exactly what we are doing here. It's sometimes used for performance, like if computing the Hessian would take too much time or inverting the Hessian would take too much time, then you just use some faster approximation of this. Okay, that's usually where quasi-Newton methods come up. In the case of non-convex energies, we have to do it anyway because Newton's method wouldn't work on non-convex cases, as we discussed before. So we have to use the quasi-Newton anyway. Sometimes it's also called modified Newton methods. Okay, so quasi-modified Newton. And already here, even just adding the multiple of the identity, even here we already modified Newton a little bit. Okay, it's no longer the exact Hessian. The exact Hessian works beautifully. So pure Newton works beautifully for convex potentials, for convex objective functions. So what projective dynamics essentially means is that you use this as your quasi-Hessian. You use some coefficient kt and you use gt transpose gt. That's it. Okay, so you use this matrix and let's call it A for a lack of creativity. Though even I think that's how we also called it in the paper, so it's also for consistency. And that's what it is. That really means that you basically ignore the Hessian of the energy and replace it with a 9×9 identity matrix times some scalar. Okay, maybe I should make it a little bit nicer by saying that this will be the WT still makes sense here, and the KT would be some coefficient which I can choose per element. Okay. So in some sense, you can view projective dynamics as reducing the Hessian of the material model to just an identity matrix times some constant, this constant KT. Okay? And the way you then work with this is the same. You just plug it into your Newton code. The only thing is that you basically hack the Hessian and you just use the different Hessian. The rest of the code is exactly the same. You have some question?
Yeah. I guess maybe I was reading the wrong paper yesterday. The one from 2014, from Pennsylvania.
Yep. And EPFL, right?
A separate cost function for the material constraints and one cost function for your implicit.
Yeah, let's bring it up. I'm pretty sure we're reading the right paper. Probably reading the projective dynamics paper, this one, right?
Yes.
Yeah, so that's the original projective dynamics paper. And the formulation here doesn't look anything like what I just said.
Okay.
It doesn't, not at all, okay?
Because I wasn't thinking until this morning, like, oh, but that was just the first hit on the search. I thought, oh, there's probably a more recent one.
Yes. And it's not at all obvious how this relates to the formulation I just explained, but they are equivalent. This equivalence is actually explained in the paper that we put on arXiv, but it will be presented at SIGGRAPH too, and that is, that's this one. That's where it's explained how exactly is it equivalent, or why exactly this is true, why it's equivalent to the previous formulation. You can completely forget about the old paper if you want. I mean, there are some nice points, but if you just want the fast version of the story, that's what I just told you.
So I guess something I missed about the previous topic is how did you form H tilde? Or are you about to talk about that?
Going back to the definiteness fixes, how do we get the H tilde?
Yeah.
Oh yeah, sure, I can explain. Yeah, I was a little bit too quick. So you get the HT, right? That's your Hessian. That's a code that depends on your material that you have to figure out. Okay. Then for the HT you do eigen decomposition. Okay. So you do Q. You know what? Let me drop the T's because I don't want to be writing T's everywhere. So let's just say it's H. Okay. So you do Q transpose lambda Q. That's an eigen decomposition, right? The lambda is a matrix of eigenvalues, lambda 1, lambda 2, up to lambda 9, right? Some of them can be negative. That's the problem, okay? What you're going to do, you're going to replace it with lambda tilde, which is clamping, okay? So you take the max of lambda 1, 0, for all of them, okay? Max lambda 9, 0. Okay, if it's a negative number, just replace it with 0. Some people prefer instead of 0 put there some small epsilon like 10 to minus 5 or something like this, if you are trying to get directly a positive definite matrix. But that's a detail that should not matter too much. Well, and then you get your H tilde as the exact same Q, but using the lambda tilde, the clamped lambda. Come on, well, like this. And then, of course, I omitted the T subscript here, but all these depend on every single element. So for every element, you do that separately. That makes sense?
Yeah. So it's still fast enough, like if you have a ton of elements, to still run like a decomposition just because it's small. Even
yeah, I
if
mean,
there's a lot of elements.
it costs you something, right? It's a 9 by 9, it's a 9 by 9 dense matrix. I mean, these days, really, the read of the matrix and writing it back will be probably costing you more than the eigen decomposition. There is some overhead to it, but it's not horrible. And if you want to really optimize this, then you can, because like for the Corot, I think that's what you can find in the Stanford papers. They basically figured out how to make this more efficient for specific. The computation of the eigen decomposition you can make more efficient if you assume some knowledge about the size. But it's kind of fine-tuning, I would say.
Okay.
Right, it's a 9 by 9, so technically speaking, the cost is constant, right? And asymptotic complexity doesn't matter. But before the point here, that was not asymptotic. That was not just a constant thing, right? This is 9 by 9. The cost, even if it's 9 by 9 cubed, 81 cubed, or no, it would be actually 9 cubed, right? That's just a number. Here in the previous case, I was saying, hey, be careful not to store these zeros for all the columns, because that would be n. So that would scale as you scale your model. That's not good. Now, if you go to projective dynamics, then actually it becomes much simpler because you are actually not even computing this to begin with. You just say, hey, let's just definiteness fix it immediately, okay? So let's just replace this with an identity matrix. The only slightly tricky thing is that you can still pick like a weighting factor for each of them. What the easiest thing to do is to just take the stiffness of the element, right? When you have the lambda parameters, if you have some material model, it usually comes with the mu and lambda. So you can just say your mu is this KT. There are some fancy ways of doing this. They are explained in the newest sentence paper, the hyperelastic, or the quasi-Newton methods for hyperelastic materials. Mm-hmm.
So the A matrix has nothing to do with the material model, like no matter what material model you have, you will get the same.
So that's almost true. It has almost nothing to do with the material model except for these K parameters, okay? So how that would matter is that, for example, if you have a bunny, and the bunny had very stiff ear, okay, that you say, let's say I want this ear to be super stiff, and the rest of the bunny, I want it soft, okay? Then this stiff versus soft should reflect itself in the value of the KT, okay? The KT for the tets in the ear, the KT would be high, would be like 1,000 or something, and for the soft ones, this would be like 1, something small, okay? So this still depends a little bit on the material, but you are right that you can ignore the specific material model. There are some nuances too, that for some types of material models, you actually don't even have to do line search. That's kind of the formulation the 2014 paper was using. So there are some special properties of certain materials, but you can just consider these details. That makes sense, Jing? So yeah, as I said, every element comes with some material parameters, right? So you can just pick the bulk modulus, the overall resistance to deformation as this parameter. And then again, there are better ways to kind of pick this case. It turned out that it actually didn't matter all that much. And then this is not this is also not a usual situation too. Sometimes you need this, but sometimes more frequently you probably simulate a homogeneous object where the material parameters are kind of more or less the same all over, in which case this K is moot. Okay, so and then the one advantage of projective dynamics is that you don't have to worry about computing the Hessian of your material model. Okay, so you don't have to worry about implementing the second derivatives. Just not a disaster, but it takes some work. So if you don't have to do it, that's good. And there is another, and that's the actual significant advantage, is that the main reason for projective dynamics being useful is that this matrix is constant. In the sense it independent of x. So if we go back, you see here, this thing is evaluated at the current deformation gradient, which depends on x. It depends on the current deformation. Okay, so that means that every step of your Newton iteration, you have to be re-evaluating this. Okay, you need to do a call to your derivative functions, then you need to multiply this. You can implement this in an intelligent way, so this is not like using too much compute power and so on, but you still have to be recomputing it. Okay. With projective dynamics, you don't have to, because there is nothing that depends on x anymore. Okay, and that's really the reason for why projective dynamics is useful, is because then what you can do is that you can prefactorize this matrix. You can do a sparse Cholesky factorization of this matrix, and that you just compute once, okay, and then you just keep reusing it over and over again. So that means that at runtime, you will only be doing the forward and backward substitutions, like when we talked about the direct solvers. And that's much faster than doing the factorization inside the Newton solve. Okay? So in summary, projective dynamics is using an aggressive approximation of the Hessian. So it doesn't converge as fast as Newton's method. Okay? But it has the advantage that you can prefactorize this projective dynamics matrix, this A matrix. So that means that every iteration is going to be much faster. So you can actually do more iterations for the same amount of time as one iteration of Newton's method. And especially when you don't care about super accurate solution, like in real-time physics, if you don't need to converge to like super accurate solution, then this will give you a significant advantage over running Newton's method. All right. So that's the end of the technical points I wanted to make. Any more questions on the technical part? So I guess in the remaining time, what I wanted to do was to do a little summary of the course and give you some pointers for next courses and stuff like this. So there were basically two main parts, right? There was the practical part, the projects, and that was the theoretical part, these lectures. I just wanted to say a few comments on the projects, even though we already went through all of them. Overall, I was quite impressed with what you guys did. The one thing I wanted to mention today was that if you are kind of slightly unhappy about how it went, if you feel like, oh, if I now could do it all over again, it would be so much better because I didn't do it right, maybe you picked the wrong libraries or something like this. So that's actually exactly what I wanted, okay? that's where the learning point comes, okay? Because this really is a practice. This is a course work, right? If this happened in a company, that would probably be bad, right? If you wasted time and you said, oh, now we kind of need to go back and redo it. If you like spend some funding and stuff, even like research project, this matters, right? But in course project, this is kind of the ideal outcome, I think. If you did something in a way that you know that next time you can do it in a better way. If something didn't work, that's actually in the long run, it's more valuable than the things that did work, right? Some things did work for you, and that was great because you got some nice results out of it. But I think ultimately more valuable is the stuff that didn't work, and you learn something from that. And if you know how to do it better next time, then I think that the project's kind of fulfilled their purpose. A related remark, kind of philosophical, is that it's not like super successful people would be never making any mistakes, right? That they would get it right on the first try. That's not the case. If some people are very successful, they are successful because they can quickly recover from their mistakes. That means they can quickly find them and correct them. That applies not just to programming. That's probably a more broader thing. And then there were these project reports I made you write, these like summary statements and so on. That's mostly for you, really, so that you, a year ahead from now, that you remember what did you do for the class, what did you learn, because especially these things like what worked and what didn't work, right? There is some lessons learned, which now you have them fresh on your memory. A year from now, you will forget about all this. But since you have it written down, then you can just easily go back and just refresh your memory. And that's something I found to be incredibly useful, because if you don't write something down, it doesn't have to be a year from it can be 10 years from now, you will encounter a similar problem. And you'll be like, oh, wait a second, I did something like this. What was it, right? So if you have it written and stored on the cloud, so it will never disappear. So you can always go back. The same is true, by the way, for these lectures, right? Also, we'll keep them on YouTube. So if there's something you need to remember long time in the future, you're working on something and you're like, oh, wait a second, we had this in the class, you can always go back to YouTube and kind of get back to the details. Then there was the theory part. So let me quickly summarize kind of what I would like you to remember from this course. There's lots of details, right, which you should forget unless you are like working on a project. Some of you will be, right, for your PhDs and stuff. You will be doing exactly this, in which case this will be fresh on your memory. If not, then I would just like you to remember a few key things, okay? I'd like you to remember what is the Hamiltonian, because this year I was putting focus on the Hamiltonian formulation of mechanics, because I find it super cool and super useful for physics-based animation. So the Hamiltonian is a function of positions in the generalized momenta, the P, which is the sum of the potential plus sum of the kinetic energy. This is, by the way, just our like 101 view to the Hamiltonian. If you talk to a physicist, the story will get much more complicated because the Hamiltonians are used in quantum mechanics too and so on. This is just our like basic Newtonian mechanics. But the p variable, that was nothing just by velocity scaled by the mass matrix. Okay, so the p, they are called generalized momenta, but it's basically the velocity times some constant for us. For us, the mass matrix is also not changing. Okay, and we talked about how can you construct the potential and the kinetic energy either for mass spring systems or for finite element models. Okay, for finite element analysis. So you know how to construct both of these terms. Now the one thing that's also very key is the concept of the phase space. So that means you have the phase space means putting positions and velocities together, or the generalized momenta, the p together, right? And then the key thing was the equations of motion in Hamilton's form. They look like this. It's the J matrix times the gradient of the Hamiltonian of Z of t. It's a system of ordinary differential equations, ODEs. And typically you look at this as initial value problem, that you are given some initial Z0, which corresponds to X0 and P0, and you have to simulate from there. You give some initial conditions to your system, and you are essentially solving the system of ordinary differential equations. Okay, this J matrix that, as I said many times, that's the zero identity minus identity 0, and this is called the phase space. So the one thing I would like you to remember is that the motion, the Newtonian motion, is flow in phase space. Okay. By flow, I mean continuous deformation. It's like a flow of fluid, some like water or ocean or something like this. That's exactly what it is with the specific mathematical structure of taking the gradient of the Hamiltonian. You know that this is nothing but a 2n-dimensional rotation, right? And it's a constant matrix. And that's really the structure of motion according to Newton and Hamilton. We also talked some about conservation laws. So basically what it boiled down to is that there are some functions on phase space. So phase space functions. So that means phase space functions mean functions from the phase space, let's call it 2m to r. Okay, so that means that this thing is from 2m, where m is the number of degrees of freedom of my system. And sometimes there are functions f which are constant during the entire motion. Okay, so mathematically f of z of t is a constant. Okay, and we talked about the fact that these motion invariants, these functions on phase space which are constant over the entire duration of the motion, they arise from symmetries of the Hamiltonian, okay, according to Noether's theorem. Okay, so you don't have to remember the Noether's theorem, what exactly these were, but some important examples is the conservation of energy and conservation of momenta. Motion invariance. So next we talked about analytical integration, right? Because this is all good. And by the way, for some people, that's where they draw the line. That's the end of the story there, right? But we go further. We say, how do we actually compute this on a computer? So we do numerical integration, which means that you do a step like this. So so this would be still the exact integration. So you exactly integrate the equations of motion, the gradient of the Hamiltonian of your z of t. For the z of t you do not know, but you know it satisfies this ordinal differential equation. Well, if you want to implement this, then you basically approximate this entire integral with some, let me write it maybe like this, integral approximation, okay? Or let me say numerical integration. Okay? This thing you usually cannot compute exactly. In some special cases you can compute it exactly, usually not. Actually no, even in your case you cannot compute it exactly, Junior. So we always approximate the integral using some quadrature rule. Okay, quadrature means just numerical integration. And then that leads to different methods, right? There is forward, backward Euler. There is the Newmark family of integrators. There is implicit midpoint. Then there are higher order methods. There are Runge-Kutta methods, RK, Runge-Kutta methods, and there is an entire zoo of zillion different methods. All they differ in is picking a different way to approximate this integral. Okay, that's the high-level summary. Now, experience shows that if you want to be nice and stable, especially in physics-based animation, you usually end up using an implicit rule, implicit integration, which means that this integration rule depends on the outcome, on the zk plus 1. So you don't get an explicit update rule where you can just easily compute zk plus 1, but you get actually a system of nonlinear equations you have to solve for zk plus 1. And usually rewarded by stability and good properties of the integrator. Usually, not always, okay? But in phys-based, that's what I end up doing ever since like Borov-Wittgen or even earlier Dmitry Terzopoulos. So that, all right. And iterative methods, The direct solvers, that was the LU, Kolasky, typically Sparse, the iterative methods, that was the conjugate gradients method, and so on. And now once you are down here, then you have to be mindful about numerical linear algebra if you care about things being fast, which we usually care about. And then we talked about finite elements, which is a more principled way of creating discrete approximations of the potential energy and the kinetic energy. Okay, so that's really the one slide summary of the entire course. I'm going to maximize this. So what would be the next steps? I think the next logical step would be to go to PDEs, partial differential equations. which are used for solids too, but are especially important for fluids. Okay, so in fluids you have Navier-Stokes equations, and you also typically use different discretization. You use Eulerian discretization, Eulerian grids. Okay, so some courses I can point you to is the new scientific and data computing course. Previously, this used to be called Advanced Scientific Computing. It comes in two versions, 1 and 2. The number 1 is offered in the fall, and the number 2 is in the spring. The fall one, that will be taught by Mike Kirby next year, and the spring one, that will be by Hari Sundar. So scientific computing is essentially like the serious version of this. Then, like here we are kind of simulating, in physics-based we are kind of simulating things for the visual effect. Okay, in scientific computing they are planning to build a bridge, and they want to compute whether the bridge is or is not going to fall down if an army of soldiers walks on it, and it's going to be resonant frequencies and that kind of stuff. It usually need to have more patience. That the patience can be compensated by running on supercomputers. That's my 1-minute summary of scientific computing. So learning about partial differential equations and Navier-Stokes and fluid simulations would be a good next step. Specifically for graphics, you can look at this one, 69, 67, special topics in numerical simulation. That's taught by Jem Yüksel. And it's usually offered in the fall. I'm not exactly sure what his plans are. All the stuff is being restructured. By the way, you know what exactly is going to be in this course is that's still a topic of discussion. I was just yesterday in some discussions what should be put there. So that also serves like all the robotics people and data science people and so on. So stay tuned. I guess this is continually being updated. So Jem is a good person to talk to about fluid simulation. He has worked on that. There is another kind of next step which is beyond this class, and it's probably even beyond computer science actually. But I just wanted to show that to you. I think I mentioned that briefly at some point. So essentially the entire physics-based animation, or let me explain it like this. Go here. The entire physics-based animation basically takes physics and uses it in computer science to do some nice animations. Okay, that's what this course was about. Okay, scientific computing, the same kind of pattern. Okay. Something that came up very recently in 2009-ish is actually the opposite arrow. Okay, what do I mean by that? Using computer science to advance physics. I mean that, if I say this generally, that probably has been done before, but what I specifically mean is this science paper, Science 2009 paper, Distilling Freeform Natural Laws from Experimental Data. I can explain you quickly what they did. They took a mechanical system and put some markers on it, okay? Made it move, gave it some, just made it move, spin it, actual physical systems, like actual like steel bars or something like this. And then captured these markers using some motion capture setup. Got a sequence of trajectories, measured some data, and then the magic happens in this arrow when they just fed it into some giant, essentially machine learning system, which essentially learned the laws of physics from the data. Okay, so this whole paper talks about what did it discover. In this case, it discovered the invariance laws. It discovered the Hamiltonians and so on. So that's essentially, I find it extremely exciting. When I talked to some Caltech people, they said this might be the way to go on like the quantum level. When you go to like the atomic particles and so on, these laws get very complicated. So it might be that the humans might no longer be able to formulate these laws, like the Hooke guy, right? And all these like laws that essentially humans formulated, right? Maybe now we need computers to formulate these laws. So that's kind of looking into the future of this field. So how computer science can feed back into physics. I recommend you, if you are interested, I recommend you reading this paper. You will find there all these things we talked about, the Hamiltonians and potentials and all these things. So if you paid attention, you should be completely ready to read papers like this, even though that's really going into physics. Okay, so that's, I guess, just two more, I guess, organizational things. Please fill in the evaluations. I know that the charts strongly agree, disagree, and stuff. That's not so much fun to fill in. What is good, what I would really appreciate, some feedback. There's like a text box where you can say, what did you like? What do you think could be improved? While staying realistic, right? Because all of you have different backgrounds, so there's no single way I could make everybody perfectly happy. I try my best. I'd be curious, what do you think about this recording setup? Other than the obvious fact that I know that there is this bug that I need to restart it every other time. It's anonymous to me, so you don't have to worry. There are some other courses that I'm teaching, some independent studies where I have only one student, so that is anonymous. But this one is not, so you don't have to worry about that. Even if there's something critical to say, that's okay. But it's better to be constructive rather than destructive than saying, oh, this is no good. Like, how it could be improved. But that's really that's really the main reason why this exists, how we can make that better next year. And we are constantly changing the content of all these courses, right? Even the scientific computing, they're also reshuffling things, trying to evolve this and make it better every year. Oh, and one last comment. If you guys, at any point in your career, sooner or later, want to do some internship or look for a job in some animation company, something that relates to physics-based, or even just general animation, then feel free to ping me. I will be happy to give you a recommendation. Since now I know you from the class, I saw what you did, so I can write a good recommendation letter. So if you want some companies like Disney, Pixar, Activision for games, Beta Digital, Oculus, Adobe, Vertaman, that's a small surgery simulator company in Switzerland. They are all looking for interns. So if this sounds like interesting and you would like to do this kind of stuff in the real world, then there are many opportunities out there.
I had a great question. A couple weeks ago, you pointed us to a website that was an FEA tutorial, like FEA deformation or FEM deformation.
Yep.
What was that website?
Oh.
I was looking for it and I didn't wind up with it.
Oh, I can write it. FEMDFEO.org. Let me actually look it up here.
DFO, you said?
Yep,
okay.
It's right here. Yeah, it's a really nice intro to finite elements. Much better than picking like an old book on finite elements, which has 500 pages. This has only 50 pages, and all the key things are there. Cool. Okay, so that's, I guess, all I wanted to tell you. Any more questions? All right. In that case, thanks so much for taking this course, for being here, for all the good questions. That was fun. And we can end here. Thanks.